The remainder and factor theorems. Let P of x be a polynomial with integer coefficients. Then any integer 0 of P of x is a divisor of the constant term of P of x. In saying that, if a polynomial has integer coefficients, that does not imply or necessarily imply the existence of integer zeros or any zeros at all. What this is saying is that if the polynomial has integer coefficients and it has an integer 0 or more than one integer 0, then that 0 will be a divisor of the constant term of P of x. And this will be of help when factorizing polynomial expressions. Here's an example. Fully factorize P of x equals x to the power of 4 plus x cubed minus 9x squared plus 11x minus 4. Now, since all coefficients of P of x are integers, any integer 0 of P of x is a divisor of the constant term negative 4. So those divisors are 1, 2, 4, negative 1, negative 2, negative 4. And we're going to test those using the factor theorem. So let's try P of 1. So 1 to the power of 4 plus 1 cubed minus 9 times 1 squared plus 11 times 1 minus 4 gives us 0. Hence, x minus 1 is a factor of P of x. Next, we divide P of x by x minus 1 to find the quotient using long division. Now, I haven't shown that here because it takes a lot of space and a lot of time. However, x to the power of 4 plus x cubed minus 9x squared plus 11x minus 4 divided by x minus 1 gives us x cubed plus 2x squared minus 7x plus 4. And I'm going to call this Q1x, as in sort of the first quotient. It's going to use the letter Q again later on. And we're going to repeat the process to see if we can find any more factors. Now, the constant term is positive 4. All coefficients are integers, and we can use the property in the first point, again, to see if we can discover any more factors. So the factors of, or the divisors of positive 4, or plus 4, 1, 2, 4, negative 1, negative 2, negative 4. We're going to test those using the factor theorem on Q1 of x. Again, the first one's x equals 1. We can try that first. And if that happens to work, then we just repeat the process again. So we'll try P of 1, 1 cubed plus 2 times 1 squared minus 7 times 1 plus 4. We get 0, hence x minus 1 is a factor. But this is another factor, even though it's identical to this factor here. So this implies x minus 1 has multiplicity at least 2, in fact. Next, we divide Q of x, or Q1 of x. I'll just fix that now. So that's Q1 of x there. So divide Q1 of x by x minus 1 to find another quotient, Q2 of x. So again, we use long division. So x cubed plus 2x squared minus 7x plus 4 divided by x minus 1. And this time we get a quadratic. So x squared plus 3x minus 4. We'll call that Q2. Let's repeat the process again. Thankfully, because it's a quadratic, and this one's easy enough to factorize, we factorize Q2 of x, we end up with x squared plus 3x minus 4. We don't need long division for this one. This one we can just factorize by inspection. And that's x minus 1 multiplied by x plus 4. Now combining these four factors, so I'll just underline those. So we have 1 there, and we've got 1 there and 1 there. Putting that all together, we have P of x is equal to x minus 1 in brackets multiplied by x minus 1 in brackets multiplied by x minus 1 in brackets multiplied by x plus 4. So therefore, P of x is equal to x plus 1, sorry, it's x minus 1 all cubed multiplied by x plus 4.